Okay, I guess we can start now. So first of all, thank you all for coming to this talk. I also want to give special thanks to the organizers of Vox Days Belgrade. I hope that this conference will become a tradition here. So just few short words about me. Who am I? My name is Martin. I'm currently working as a software consultant, self-employed. I'm also one of the board members of the Bulgarian Java user group, where we organize seminars throughout the year. We also have a large conference that we organize in Sofia. And from time to time, I'm also contributing to the OpenJDK platform and several other projects. So in this session, I'll tell you a short story. And this story is about the evolution of the security architecture in the JDK platform. So who of you has done some security programming for the Java platform? I mean, using the security manager, the access controller classes. 2, 3 people? Oh, more. About 7 people, okay. So I hope you'll enjoy this session. And in this talk, first we'll discuss what's the evolution of the security sandbox model in the Java platform. What is actually this sandbox model? Then we'll discuss shortly the supporting KPIs that are built around this sandbox model in the Java platform. And at the end of the talk, we'll discuss shortly some best practices that you need to apply when you develop your Java applications, and that you need to think about when you know already what the security sandbox model is about. Okay, so evolution of the Java security model, and basically what's the Java security sandbox model. Traditionally, many companies, both small, medium, or large, try to protect their assets by deploying different types of security assets. This could be firewalls, intrusion detection systems, intrusion protection systems, and so on and so forth. You know that basically when a security breach happens inside of a system, you have to isolate, to put one or more machines in a quarantine, and then try to fix the security issues that have arisen in this system. And in many cases, this can be pretty destructive for the infrastructure that you have. With the introduction of a number of new technologies, including Java applets, a new range of security concerns rises when it comes to browser security. And especially, one of the goals of the Java security sandbox model is to allow untrusted source code, Java source code, to be executed securely from a Java applet, or basically any other technology that would allow you to execute Java source code from the browser. And this is how this security model was introduced in version JDK 1.0. This was more than 15 years ago. So this was the initial security model introduced in the JDK platform. We had the system code, which was all of the classes in the JDK platform. And also we had one or more applets that are loaded by some particular website that you load. In version 1.0, the system code was deemed as trusted, meaning that, for example, JDK core classes could write to the file system, open a network socket, and do whatever they want. And on the other hand, applets were deemed as untrusted code, meaning that they were part of a security restriction that imposed a number of permission checks over that source code. This means that essentially all of the applets that are loaded as part of your website must be checked for some particular type of permission. For example, whether these applets can write to the file system, whether these applets can open a socket connection, and so on and so forth. And basically, this was a pretty simple model. You had just trusted and untrusted code, and that's it. No more fine-grained access control. So code was divided basically in 2 domains, as we already mentioned, trusted and untrusted, and strict restrictions are applied to the untrusted part of the source code, or in this particular case, the applets. When it comes to JDK 1.1, several new enhancements were introduced, and the biggest one of them was signed applets. So if you can think of trusted and untrusted source code, this is a very restricted model. You cannot apply, for example, you cannot say, I want these 2 applets to have these permissions and those other 3 applets to have those permissions. So the guys at Sun at that time decided to introduce the notion of a signed applet, meaning that you can sign an applet file, the jar file of the applet, with some certificate, and then you can deem that signed applet as a trusted source of information. So basically, when you deploy signed applets as part of a website, they are all trusted and they can do whatever they want with the system. So still in version 1.1, we had the notion of trusted and untrusted code, but this time just signed applets are deemed as trusted. They can do whatever they want with the system. And basically, these are the few short steps that were required to sign an applet. You have first to compile the applet and create a jar file. Then you have to generate a pair of public-private keys. Then you have to sign that applet jar with the private key and export a certificate for the public key. Up to that point, you can use a private key infrastructure and a certificate authority to request a certificate. Then you need to import that certificate as a trusted certificate into your JVM deployment. Then you have to create the policy file that specifies what does untrusted code is allowed to do with the system. And at the end, you can load and run that applet. So this was the way applets are still signed. And that was the model in JDK 1.1. And here in JDK 1.2, there is a radical change in the sandbox model. So now we don't have any more trusted and untrusted source code. We now have the so-called security manager. So does any one of you know what is the difference between a security manager and an access controller? No? Okay, so basically the security manager is an older API. And the idea behind the security manager is that it does all of the permission checking that's required for checking whether a particular piece of code is allowed to do anything with the system. For example, write to the file system, open a socket, and so on and so forth. So now, in JDK 1.2, a new model was introduced that's still being used in the JDK platform. And that model specifies that we have a particular code source. This is the location from where the applet is loaded. In that example, we have a simple applet that's being loaded from voxdays.com/demoapplet, and that's the location of our applet. So based on that location, I can specify some permissions for the applet. In the particular example, I have a snippet from a Java security policy file that specifies that I grant the permission to delete the C Windows folder, and I grant that permission to all applets loaded from voxdays.com/demoapplet. And as you can see now, the security model becomes more code-centric. Now we don't have trusted and untrusted source code. We have a security policy file that specifies what code is allowed to do whatever you want with the system. And basically, access control decisions are specified in a security policy file, as we mentioned. And there is no more notion of trusted and untrusted source code. But still, there is a new thing introduced in JDK 1.2, and that's the notion of a protection domain. So we have two particular types of protection domains. These are system and application protection domains. Do you know what a protection domain means in that sense when we don't have a trusted and untrusted source code? Any suggestions? Okay, so a protection domain basically is set during class loading. So when classes are loaded by the JVM, you set a protection domain. And that protection domain essentially represents the set of permissions that this class is allowed to do when it's loaded in the JVM. So this is a protection domain. You retrieve an instance of the protection domain for a particular class by calling applet.getClass.getProtectionDomain. And an applet here is some instance of an applet class that's being loaded by the browser, for example. So we have now a protection domain, and basically one specific thing about protection domains and the set of permissions that we have is that one permission can imply one or more other permissions. So in this example, if I say that I can delete the C Windows folder, and I specify that permission for one or more applets, then this permission implies that I can also delete the C Windows System32 folder. So one permission can imply another permission. Another thing is that one location of our applets can imply another location. So if I load an applet from voxdays.com, this means that I set permissions also for all applets that are being loaded from voxdays.com/demoapplet or / whatever you can think of. So another specific thing about the protection domain is that it is not just one. So for example, you have a WAR file, and you want to deploy that WAR file to an application server. And the source code in that WAR file uses some APIs from your Java application server. However, you specify some permissions for the WAR file, let's say some WAR file that's being loaded from voxdays.com, and you have some local permissions that you specify for the source code of the application server. So now we have two protection domains. One for the classes inside the applet, inside the WAR file, sorry, and one for the classes inside the application server. This means that the stack trace passes through multiple protection domains. And the decision taken behind the implementers of the security model decide that the active set of permissions is just the intersection of the permissions inside the two protection domains. So let's say that our WAR file is allowed to write to the file system, and the application server is not allowed to write to the file system. In that case, the WAR file is not allowed entirely to do whatever it needs to do on the application server. Okay, so that was in JDK 1.2. So what happens in JDK 1.3 and 1.4? So as you can see in that security model, we don't have any way to specify who is executing the source code. We only specify the location and the set of active permissions for that location. But in JDK 1.3 and 1.4, the guys from Sun decided to introduce what's called JAAS. Does anyone know what JAAS is? No one? Yeah? What is JAAS? Service. Okay, so you win a book. It's an open JDK cookbook. You'll take it after the session. So JAAS is Java Authentication and Authorization Service, and it extends the current security model with additional information on who is the one that executes the applet, who is the user that loads the applet into the browser. And basically now into the security policy file, you can specify additional information apart from the location of the applet. And that information is, for example, some principle that is, in this particular case, a principle is just a property of the user that loads the applet. And this principle in this particular case is an LDAP principle that has a property Cn equals Tom. So principles in JAAS basically are some properties that are attached to a subject, and a subject is just the one that loads the applet. So you can specify that the user needs to have particular properties so that he can do something with the system. In this particular case, the user should have a name of Tom so that he can delete the C Windows folder. And that's specified into the Java policy file. So JAAS essentially has two parts. The one is the authentication part, and the other one is the authorization part. And now the protection domain of a Java class contains not only information about the location of an applet, but also information about who is the user that executes the applet, and what is the set of principles or properties that he needs to have in order to do something with the system. So basically now the protection domain as of Java version 1.4 contains both the source code or the location of the file and the set of permissions represented by a list of principles that may be specified in the Java policy file. However, the authentication component of JAAS that allows the user to be authenticated and essentially some properties to be set when the user is authenticated, can be used in a much wider context, not only as part of the JDK. And essentially many Java application servers implement that model, which is pluggable, meaning that you can specify different sources of authentication information. This could be an LDAP server, a database, and whatever you can think of. But this needs to be implemented in terms of the JAAS framework. And the authorization component that we saw earlier, this one, is the one that actually extends the security model of the Java platform. Okay, so here are the core classes of JAAS. The first one, I'll start from the end, is the login context. When you work with JAAS, you create a login context that encapsulates all of the login information that the JVM needs to know in order to authenticate the current user. A login context can use one or more login modules, meaning that he can authenticate a user from one or multiple sources, for example, from a database. If authentication fails from a database, then it can fall back to an LDAP server, and so on and so forth. On the other hand, a login module contains one or more subject, and each subject has one or more principles, which are actually the properties that specify some particular information about that user. Such properties could be, for example, the email address of the user, the name of the user, and some other information. So this is a very brief review of what JAAS is. Okay, so up to JDK 1.4, we had a very well-defined flow for permission checking using the new security model introduced in version 1.2 of the JDK platform. So when the system starts up, it first needs to set the security manager. When an application server starts up or a NoSGI framework starts up, they need to provide a security manager instance that is used to check whether the system has some permissions to do something. Apart from a security manager, you also set a security policy. By default, policy information is specified in the security policy file in the JVM, but sometimes you may need to implement another mechanism for specifying permissions. Okay, so first the system starts up and sets a class load security manager. Second, when the system starts up, it needs to load classes. And during class loading, as most of you know, bytecode verification is done so that it checks that the bytecode is valid and it does not try to break the JVM. Third, when system code is invoked from a remote code, in this example, if we load an applet in a JVM that runs in a client browser, then the security manager is used to check for the intersection of the protection domains that the current applet has some permission to do something with the system. So basically what the system manager does is to traverse the current call stack of the execution thread and check whether each particular method has the permission to do something. So here is it, a very basic example of how a permission checking is being done. So you first, for example, create a socket permission. You can see a lot of places in the JVM source code and the JDK classes that do something like this. So you create an instance of a permission class that has several things. The first thing is the code source or the location of from where the source code is being loaded. Does anyone know how is this location being set and when? For example, how shall I know that this voxdays.com is the location of a particular class that runs in the JVM? Yeah, but
because we have location from where applet was loaded.
yeah, and that location applies to all of the classes inside the applet. Second of all, we also have one or more particular actions that apply to that permission. In this example, the two actions that I have are connect and accept. This means that any source code loaded from voxdays.com from ports 8000 to ports 9000 can connect and can accept connections, basically. So this means that I have a socket permission that will check whether the current source code that is being executed can actually connect or accept to anything from this location here. And of course, I may not have installed a security manager. So I may run my source code in an environment, for example, not an application server. So I won't have an instance of a security manager. In this case, system.getSecurityManager will return null, meaning that I don't have a security manager installed in my system. And if I do, if I have a security manager, then I check the current source code that executes. Just as a short recap, the security manager takes the current execution stack and checks whether each method has the permission to do this thing here, has the permission to open a socket to that location. Okay, so after permission checking is being done, either by using a security manager or an access controller. So the specific thing about the access controller is that it's a newer API, but it's being used by the security manager. So in earlier versions of the JDK platform, we had only a security manager and not an access controller class. But now you don't need to install a security manager in order to check the active permissions of a source code. You can use an access controller class directly. It has a number of static methods that allow you to do permission checking. Okay, so here is an example, the same example basically, but using an access controller class, not a security manager. So you say access controller dot check permission, and you supply a permission instance. This checks whether the current executing code has the permission to open a socket or accept a connection from that location. Also, sometimes it happens that you need to execute a source code in a privileged mode. For example, you have a WAR file that needs to write to a log file in the application server. But the WAR file does not have the permission to write to anywhere in the file system. In that case, the application server will do something like access controller.doPrivileged and supply the privileged action, in this case, the writing to a log file in the application server. DoPrivileged means that you execute, the current source code executes in an elevated mode, and that the protection domain only of the action that is applied to the doPrivileged method is checked for permissions, not above the stack trace. I mean that whenever you have an execution of this, whenever you call access controller.doPrivileged, any other source code up in the stack that calls this is ignored, and the permissions of that source code are ignored. Of course, the security manager model is customizable. For example, the Oracle database uses a custom version of a security manager to check, for example, that whether the currently executing Java stored procedure in the Oracle database can do something with the file system. And the permissions there are specified in a relational database table. You can also write your own security manager implementation, but it's very error prone. So you have to be very aware of the subtleties of the security manager API. Otherwise, even subtle bugs can introduce a lot of security issues inside your system. Okay, and now JDK 1.5 and 1.6. The current model stays the same. So we have still the security manager and the access controller classes, but we have several small enhancements. So for example, we have an introduced LDAP support for JAAS. And this is one of the most significant changes in that regard in JDK 1.6. In 1.7 and 1.8, we have also several small enhancements. And one of them, for example, is the ability to supply just a subset of permissions when you have a privileged execution of access controller doPrivileged. In JDK 1.9 and beyond, so as you know, JDK 1.9 is still not released, but as most of us expect, Project Jigsaw should be available. Does anyone know what Project Jigsaw is? No one?
Yes.
So it's basically a modularization of the Java platform. And by modularization, I mean that both the JDK core classes are split into modules. These are 5,000 and more classes in the JDK platform that need to be split into particular APIs. For example, a JDBC module, a Java util logging module, and so on and so forth. And on the other hand, developers are given the ability to build modules themselves and to install on demand these modules as part of the JVM. And this will, of course, introduce some concerns considering the current implementation of the Java security model. So now, as you can imagine, each module can be loaded either from the current file system or from a remote location. Let's say that the guys from Oracle decide that they'll implement a standard mechanism for deploying module repositories. In that case, you may need to load a module from a remote location. And that remote location must be a subject of permission checking, for example. So in that sense, the security model in JDK 1.9 must be extended with some information about the location of where a module is being loaded. And of course, permission checking should be extended additionally to modules. But the model, expectingly, should stay the same. Just a few short words about Project Jigsaw. So any questions about the security sandbox model? Okay. We're continuing with the second part. So we covered what is the initial implementation of the Java security model. However, this model is supported by a number of useful APIs that some of you may have used or some of you may be using in the future. But in any way, it's essential to just have a basic idea of what these APIs cover. So the sandbox model, on the one hand, is a very restricted model for executing the source code. As we saw, it is a subject of permission checking. And on the other side of the coin, we have a number of APIs. And here is a very short list of the APIs that covers actually most of them. We have the Java cryptography architecture. We have various utilities for either building your own public key infrastructure or using an existing one. You have the secure version of the Java sockets. You also have the Java GCC API, which we'll cover briefly, and the Java simple authentication and security layer as well. So JAAS, or the Java cryptography API, as most of you know, provides a number of utilities for working with message digest, creating digital signatures, and so on and so forth. And basically, it's a direction of the JDK to implement better and stronger cryptographic algorithms and supply them as part of the JVM. We'll not cover GCA in details. And GCA has a pluggable architecture, meaning that you do not need at compile time to have, for example, algorithms for digitally signing some piece of code. You may supply them at runtime by means of the so-called security providers. So this mechanism actually allows you to plug additional algorithms that can be used by the JCA infrastructure. The PKI utilities allow you to deal with security certificates, to create certificate revocation lists, and so on and so forth. So just as a brief recap, certificate revocation lists allow you to check whether a certificate is still valid and it's not being stolen, for example. So they can actually revoke a certificate if it's not valid. And here is a very basic flow of how certificate revocation checking is being done. So you send the certificate information to the certificate authority. It checks whether that certificate is valid, and this can happen by means of, for example, a certificate revocation list, which is just a file with information about what certificates are not valid, or using the OCSP protocol. Another thing that is part of the security APIs is the secure socket extension. This is just an SSL version of the standard sockets in the JDK platform. Nothing specific about them. The Java GCC API is an interesting thing, and it provides an alternative of secure sockets. But the way that GCC works is by encapsulating security information in a context. and it passes that context between the client and the server. It also uses token-based security services that allow you to perform the security checks. And of course, GCC API can be used along with JAAS for authentication purposes. For example, you can supply a context to the server, and the server can use the mechanisms of JAAS to check whether that information is valid and that the current user can log into the system or cannot. You have the SASL framework, which is an interesting one. It allows you to exchange security information between the client and the server. For example, the client says, I want to authenticate by email and by username. And the server says, okay, you can authenticate by these two principles or by these two properties. And it returns that answer to the client. The client says, okay, so let's start authenticating using an email and a username. So basically, the SASL framework allows you to exchange security information between the client and the server before actually performing any authentication or authorization. And SASL also continues to evolve as part of the JDK APIs, especially in terms of enhanced support for the Kerberos protocol, for example. Okay, and just to wrap up the talk, I'll give you just several short guidelines that you have to think of about when you apply that security model. For example, many of the guidelines really apply not only to the Java platform, you've heard them all. For example, SQL injection, invalid input, error handling, type safety, and so on and so forth. These are just some very general security guidelines that most of you can think of. However, when you think of the Java platform, you really need to respect the security major. For example, in my personal practice, I had to deal, for example, with the Google JSON library. So the Google JSON library is a library for parsing JSON. However, this library uses reflective APIs that are typically a subject of permission checking. And when we tried to use the JSON library as part of an OSGI framework that was using a security major, there were a number of access control exceptions that were thrown at us. And at that point, we started thinking of what could be the cause of that problem. And the reason was because the JSON source code was not aware of the fact that there could be a security major installed in that system. So what we had to do, we had to supply a patch to the folks from the JSON team that they needed to apply so that you can use JSON in a managed environment such as Java EE or OSGI. Also, you need to grant minimal permissions to code that requires them. For example, the easiest thing to do when you get a security permission exception is just to set all permissions to the source code. And this is done very widely in practice. For example, during development, the developer is annoyed that he needs to specify particular permissions, and he gives all permissions. And after that, he forgets to remove them, and the system is open for a lot of exploitation. Also, you need to sanitize exception messages. You don't need to return to the user the stack trace of the source code, because this is a very useful source of information for anyone willing to exploit your system. So that was it. Thank you. So before I give the book to the guy that won it, any questions about the security model?
What about bytecode manipulation at runtime?
Bytecode manipulation at runtime. Well, if you try to manipulate bytecode, still the bytecode that you try to execute is a subject of bytecode verification. So you still have to, even if you modify the bytecode, the JVM will still check it whether it's valid or not.
But then you need to have security manager installed.
Well, security manager does not deal with bytecode verification. It's just a higher level API. Bytecode verification is done by the JVM when it executes the source code, but it also does security manager permission checking, which is a further step in checking whether something is allowed to be done on the system. Okay. Any more questions? Okay, if not, thank you for attending this talk. I hope you enjoyed it. If you have any questions, you can ask me.